Lecture 20, The Measures of Strain. The measures of strain involve changes in length, changes in angle, and changes in volume. Let's start with changes in length. Suppose a line with initial length Li is stretched to a final length Lf. The elongation, E, is the final length of the line minus the initial length, divided by the initial length. It is a value that ranges from -1 to a positive number. An elongation of 0 means no change in length. The stretch, S, is the final length of the line divided by the initial length. It is also equal to 1 plus the elongation. The stretch ranges from 0 to a positive number. A stretch of 1 means no change in length. And the quadratic elongation, lambda, is the square of the stretch. It is a value that ranges from 0 to a positive number. A quadratic elongation of 1 means no change in length. In this figure, the black square is the undeformed configuration, and the red polygon is the deformed configuration. For changes in angle, we have two measurements. The angular shear, psi, which is the change in angle between two originally perpendicular lines. And the shear strain, gamma, which is the tangent of the angular shear. Changes in volume are defined by the dilation, delta, which is the final volume minus initial volume divided by the initial volume. Another measure of volumetric strain is the volumetric stretch, which is the final volume divided by the initial volume. If S1, S2, and S3 are three orthogonal stretches, the volumetric stretch is S1 times S2 times S3. Finally, we need to talk about strain rate, or eta, which is strain divided by time. Strain is dimensionless, it does not have any units. Therefore, strain rate has units of 1 over time. The metric unit is 1 over second. These examples illustrate better what strain rate means. Suppose the strain in a body is 10%, or 10 to the minus 1. If in an experiment this strain is induced in 1 second, then the strain rate is 10 to the minus 1 per second. Now, if the same strain is induced during an experiment with a duration of 4 months, or 10 to the 7 seconds, the strain rate is 10 to the minus 8 per second. Finally, for a strain rate of 3 times 10 to the minus 14 per second, it takes 3 times 10 to the 13 seconds, or about 1 million years, to reach a strain of 10 to the minus 1. This figure shows the geological strain rates. The vertical axis to the left is strain rate in 1 over second. The vertical axis to the right is the time it takes for the strain rate to reach a strain of 10%. Meteoric, explosive volcanic events, and earthquakes have very high strain rates from 10 to the 2 to 10 to the minus 4 per second. Intrusions have strain rates of 10 to the minus 4 per second, for small intrusions, to 10 to the minus 14 per second, for large kilometer-size intrusions. Non-indurated sediments deform at strain rates of 10 to the minus 6 to 10 to the minus 12 per second. While indurated sediments have lower strain rates between 10 to the minus 12 to 10 to the minus 18 per second. Regional downwarp or uplift events have slow strain rates of 10 to the minus 14 to 10 to the minus 19 per second. Salt is a rock material that flows much more than other type of sedimentary and crystalline rocks. However, the strain rates of salt flow vary quite a lot, from slow rates of 10 to the minus 14 to 10 to the minus 16 per second for buried salt diapirs, to faster rates of 10 to the minus 9 to 10 to the minus 12 per second for emergent salt sheets. The strain rates of tectonic deformation are in general between 10 to the minus 14 to 10 to the minus 16 per second. However, the strain rates one can possibly reach in a laboratory are much higher, from 10 to the 1 to 10 to the minus 8 per second. The lower range of strain rates in the lab corresponds to a 4 months experiment that reaches 10% strain. This is a problem when modeling tectonic structures in the lab. To learn more about these concepts, please read Chapter 2 of Fossen, and check his e-learning module on deformation. And answer these questions.